Good evening, class. This is Lionel Brown reporting live. Today is October the 15th. I'm representing the class of 2003. Y'all know how we do it. I'm about to read chapter 8. Alright. The Earth of Chemistry. Starting now. Scientists have long sought to understand the universe by examining increasingly small parts of it. Scientists have studied parts as long as the planet Earth. They have classified the material that makes up the Earth into solids, liquids, and gases. In their quest to better understand Earth, science search for smaller and smaller parts have been turned their attention to studying atoms and their interactions. Now I'm going to do the chapter online. 8.1 Matter, atoms and elements, atomic structure, isotopes, solid liquid gases. 8.2 Combination of atoms, electron energy levels, chemically bonds, chemical formulas and mixtures. And on page 138 we also have a beautiful picture of the Earth chemistry. You have ice, you have smoke. It looks real tastic. Okay. Now 8.1 Matter, the section objectives. State the distinguishing characteristics of an element. Describe the basic structure of an atom. Define atomic numbers and mass numbers. Explain what an isotope is. Compare solids, liquids, and gases. Every object in the universe is made up of particles of some kind or substance. Scientists use the word matter to describe the substance of which an object is made. Matter is anything that takes up space and has mass. The amount of matter in any object determines mass of that object. Scientists are also able to identify the kind of matter that makes up the substance by observing the properties of the substance. All matter has two major distinguishing properties. Physical properties are those characteristics that can be absorbed without changing the components of the substance. For example, physical properties include density, color, hardness, freezing point, boiling point, and the ability to conduct electricity. Chemical properties are those characteristics that describe how a substance interacts with other substances to produce different kinds of matter. For an example, a chemical property of iron is that it interacts with oxygen to form rust. A chemical property of helium is that it usually does not interact with other substances. Understanding the chemical properties of a substance requires a basic information about the particles that make up substance, atoms, and elements. All matter is made up of elements. An element is a substance that can be broken down into simpler form or by ordinary chemical means. Figure 8.1 shows the most common elements in the Earth crust. Notice that there's a universal understood symbol of one of the two letters that represents each symbol. Over 90 elements occur naturally in the Earth. Another dozen or so have been created in the laboratory. Of the natural elements, only 8 make up 98% of the Earth's crust. In fact, two elements, silicon and oxygen, make up almost 75% of the Earth's crust. Elements consist of atoms. An atom is the smallest unit of an element and has all the properties of the element. The word atom comes from a Greek word for invisible. You can identify elements by its atoms. The atoms of any one element are significantly different from the atoms of any other element. Atoms can be broken down into smaller particles by ordinary physical or chemical processes. An atom is so small that it's the size of a single atom. It's difficult, and it's very difficult to imagine. To get an idea of how small an atom is, look at the thickness of this page. An atom is millions and millions times smaller than this. Atomic structure. As tiny as atoms are, they are made up of even smaller parts called subatomic particles. The three major kinds of subatomic particles are electrons, protons, and neutrons. Electrons carry a negative electrical charge, protons carry a positive charge, and neutrons are neutral, having no net electrical charge. The subatomic particles are arranged in a similar way within all atoms. The protons and neutrons of atoms are packed close to one another. Together they form the nucleus, a small region in the center of an atom. Because neutrons do not carry an electrical charge, the protons give a nucleus a positive charge. Compared with the size of the whole atom, the nucleus takes up about the same space as a gumdrop in a football stadium. The electron of an atom moves in a certain region of space around the nucleus known as the electron cloud. Because unlike electrical charges attract, the negatively charged electrons are not to be attracted to the positively charged nucleus. Consistently, the electrons tend to remain relatively close to the nucleus of an atom. However, the constant motion of the electron keeps them from falling into the nucleus. An atom of a specific element is distinguished from the atoms of all kinds of elements by the number of its protons. For example, an atom of the element lithium contains 3 protons. No other element has 3 protons. Atomic number. To help in the identification of elements, scientists have assigned an atomic number to each kind of atom. All atoms of any element have the same atomic number. The atomic number is equal to the number of protons in the atom. An uncharged atom has an equal number of protons and electrons, and so has neither a positive nor a negative charge. Therefore, the atom is electrically charged. Thus, the atomic number also equals the number of electrons in the uncharged atom of that element. For an example, the atomic number of oxygen, which is 8, shows the oxygen atom has 8 protons and 8 electrons. The atomic number of 1 for hydrogen shows that each atom has 1 proton and 1 electron. Atomic number is one of the components listed for each element in the periodic table. The periodic table is a system for classifying elements. Mass number. Each atom has a mass number. The mass number of any atom represents the sum of number of protons and neutrons in the atom. The actual mass of the subatomic particle is so small that rather than grams, a specific unit called the atomic mass unit is used. Protons and neutrons each have an atomic mass close to 1 U. In contrast, electrons are much less massive than protons and neutrons. In fact, it takes a combined mass of 1840 electrons to equal a mass. You playing it dope. Because electrons add so little to the total mass of an atom, their mass may be ignored in calculating the mass of an atom. You can use an element's atomic number and mass number to determine the number of protons, neutrons, and electrons in an atom of the element. For instance, if you find sodium on the periodic table, you will see that the atomic number is 11. Since the atomic number equals the number of protons or electrons, sodium has 11 protons and 11 electrons. Notice the sodium has an atomic number of 22.99, which rounds to 23, the mass number. Since the mass number equals the sum of protons and neutrons, the mass number minus the atomic number equals the number of neutrons. Therefore, subtracting 11 from 23, you will find that sodium has 12 neutrons. What is the number of protons, electrons, and neutrons for nitrogen? Isotopes. Although all atoms of a given element contain the sum of numbers of protons, they do not always contain the same number of neutrons. Because the mass number is equal to the sum of protons and neutrons in the nucleus, each additional neutron increases the mass number. Atoms of the same element that differ from each other in mass number are called isotopes. Isotopes of any given atom have the same number of protons but a different number of electrons. Hydrogen is an example of an element with several isotopes. All hydrogen atoms have the atomic number 1. That means the hydrogen atom has 1 proton in its nucleus and 1 electron moving around the nucleus. However, some hydrogen atoms also have 1 neutron in the nucleus. Because the neutron adds 1 unit to the mass, hydrogen atoms with 1 neutron in the nucleus have a mass number of 2. A very rare form of hydrogen has 2 neutrons in its nucleus. It has a massive number of 3. Figure 8.4 shows the 3 isotopes of hydrogen. Solids, liquids, and gases. There are several ways to classify matter. One way is to classify it into 3 physical forms: solid, liquid, and gas. The particles that are made up of a solid are packed tightly together in fixed positions and are not free to move very much. Therefore, a solid has a definite shape and volume. A liquid has a definite volume but does not have a definite shape. Instead, a liquid takes the shape of a container that holds it. The particles that make up a liquid are also tightly packed, but they are free to move in relation to any other solids. A gas does not have a definite volume or shape. The particles of a gas are farther apart and move faster and more freely than those of liquids. A gas is thus a formless collection of particles that tends to expand in all directions at the same time. If a gas is not confined, the space between its particles will continue to increase. Look at figure 8.5, which shows the relative motions of atoms in solids, liquids, and gases. To melt a solid material, heat must be added. Heat causes the particles in the solid to move faster. When enough energy has been added, the individual particles move so rapidly that they break away from their fixed positions in relation to each other. The result in the material becoming a liquid. Additionally, heat causes the particles in the liquid to move even faster, the result of the formation of gas. That's the end of chapter 8, unit 1. Now we go to chapter 8, point 2. Combinations of atoms. Elements rarely occur in pure form in the Earth's crust. Instead, they generally are found in combination with other kinds of elements. When the atoms of two or more elements are chemically united, the resulting substance is called a compound. A compound is a new substance with properties different from those of elements that compose it. For example, water is a compound formed with atoms of hydrogen and oxygen. Combined sodium chloride table salt is a compound of sodium and chlorine atoms. The smallest complete unit of a compound is called a molecule. In a compound water, for example, every individual water molecule is made up of 2 atoms of hydrogen and 1 atom of oxygen. Some elements exist naturally as a diatomic molecule. Molecules are made up of 2 atoms. For example, hydrogen occurs naturally only as a diatomic molecule. The oxygen. Oxygen that is not part of a compound also occurs as a diatomic molecule. The oxygen in the air you breathe is a diatomic molecule. The O is a notation in the symbol for oxygen. The subscript 2 indicates the number of atoms of oxygen. Electron energy levels. Different kinds of atoms join together and form compounds based upon the weight their electrons on the rings. Remember that the electrons in the atom move in an electron cloud outside the nucleus. Within the electron cloud of an atom, electrons are arranged in energy levels. The electrons in each level have a specific amount of energy, and each energy level can hold only a certain amount of energy, and each energy level can hold only a certain amount of electrons. For example, the first energy level can hold a maximum of 2 electrons, and the second can hold up to 8 electrons. An electron occupies only one energy level at a time. Although it may go to higher or lower levels, also the electrons of an atom may float several different levels. For example, the electrons of an atom, such as radium, may occupy 7 levels. However, many energy levels are occupied in any atom. The outmost level can never hold more than 8 electrons. What is the number of electrons that an element with one energy level can have? Not all atoms have the maximum number of electrons in their outermost energy level. However, the most stable atoms are those in which the outmost energy level is full. In other words, the outmost level in these atoms holds the maximum number of electrons are 8 electrons. Atoms with filed outer energy levels do not easily lose or gain electrons, and so they do not easily form compounds with other elements. Atoms of certain elements give up electrons more easily than atoms of certain other elements. Atoms of only 1, 2, or 3 electrons in the outermost level give up electrons easily. The electrons that have these limited number of electrons in the outermost level are the same elements that have metallic properties and are classified as metal. Examples of metals are aluminum, copper, gold, iron, lead, and tin. Metals have a number of useful characteristics. Most metals are good conductors of heat and electricity. Many metals are malleable, which means that they can't be harmed into thin sheets. These metals also ductile. They can be drawn out into wire. Atoms with 4, 5, or 6 electrons in the outermost level do not lose electrons easily. These elements without metallic properties and are classified as nonmetals. Carbon, nitrogen, and oxygen are examples. Chemical bonds. The atoms that combine to make up a compound are held together by forces called chemical bonds. A chemical bond is produced by the interaction of electrons from the outermost energy level of 2 or more atoms. Scientists can predict which kinds of atoms will form chemical bonds with each other. They compare to the number of electrons in the outermost energy level of the atoms with the maximum number possible for that energy level. For example, a hydrogen atom has only 1 electron in its single energy level. Because this one energy level can hold 2 electrons, you can predict that hydrogen will accept another electron if it is available. Atoms can form chemical bonds by sharing electrons or by transferring electrons from one atom to another. In both cases, the attraction that joins the atom is the pull of an electrical charge. When electrons are transferred from one atom to another, the bond is an ionic bond. Ionic bonds. A compound formed through the transfer of electrons is called an ionic compound. Most ionic compounds are formed by the transfer of electrons from a metal to a non-metal. A familiar example is sodium chloride or common table salt. A sodium atom has 11 electrons and 2 electrons in its first energy level. 8 electrons in its second energy level and 1 electron in its outermost energy level. A chlorine atom has 17 electrons with 2 electrons in its first energy level, 8 electrons in its second energy level, and 7 in its outer level. With only 7 electrons in its outer energy level, chlorine can accept 1 more electron. Because of the number of electrons in their respective outermost energy levels, sodium atoms have a strong tendency to lose 1 electron and chlorine atoms tend to gain 1 electron. Therefore, a sodium atom will give up an electron to a chlorine atom as shown in figure 8.7. When an electron is transferred from one atom to another, both atoms become electronically charged in an ion. There's an atom, a group of atoms that carries an electrically charge. A sodium atom becomes the atoms that carries an electrically charge when it gives up an electron. The loss of an electron leaves a sodium atom with 11 protons in its nucleus but only 10 electrons. In a similar way, a chlorine atom becomes an ion when it gains an electron. The additional electron gives a chlorine atom 18 electrons, 1 more than its 17 protons. The extra electron changes the neutral chlorine atom into a negatively charged chlorine ion. As you have read, sodium and chlorine ions combine and form the compound sodium chloride. Positively charged sodium ions and negatively charged chlorine ions are held together because opposites charged atoms attract one another. The attraction between the sodium and the chlorine atoms creates a crystal arrangement with a definite cubic shape. The arrangement can easily be seen by observing some table in the palm of your hand. Covalent bonds. A bond caused on the attraction between atoms that share electrons is a covalent bond. Water is an example of a covalent compound. At the same time, the oxygen atom shared 2 of its electrons, 1 with each hydrogen atom, giving each hydrogen atom a stable number of electrons in the outmost level of electrons. Thus, a water molecule consists of 2 atoms of hydrogen combined with 1 atom of oxygen. Each covalent compound consists of only 1 kind of molecule, just as each element consists of only 1 kind of atom. When atoms share electrons, the positive nucleus of each atom is attracted to the negative electrons being shared. The pull between the positive and negative charges in the force that keeps the atoms joined. In diatomic gases, such as nitrogen and oxygen, the most abundant gas in the Earth's atmosphere, there are covalent bonds between the 2 atoms of a diatomic molecule. Because the nuclei are identical, they each pull with the same strength on the shared nucleus. In a compound, the covalent bonds are between 2 different kinds of atoms. The nucleus of one atom pulls more strongly than the other. The electrons are shared by remaining closer to the nucleus that pulls more strongly. In a water molecule, for example, the oxygen nucleus attracts the electrons more strongly than those near the hydrogen's nucleus. As a result, the molecule has a slightly negative charge and its oxygen and a slightly positive charge and its hydrogen in. The various molecules that make up a covalent bond, such as water, are usually held together by weak forces of attraction. These forces are far weaker than powerful attraction between ions in an ionic compound, such as sodium chloride. For this reason, ice and covalent compounds melts at a much lower temperature than does a sodium chloride in an ionic compound. Chemical formulas. In any given compound, each covalent or ionic, the elements that make up the compound are also found in the same proportion. Therefore, a compound is represented by a fixed chemical formula. A chemical formula indicates what elements the compound contains. It also indicates the relative number of atoms in each element that is present. The chemical formula for water is H2O, which indicates that each water molecule consists of 2 atoms of hydrogen and 1 atom of oxygen. And the chemical formula subscript number is used oh man. It is used in the example in the chemical formula for water. The subscript number 2 after the H indicates that 2 atoms of hydrogen are in each molecule of water. Mixtures of the earth elements and compounds are generally found mixed together. A mixture is a material that contains 2 or more substances that are not chemically compound. The substances and a mixture keep their individual properties. Therefore, unlike a compound, a mixture can be separated into parts by physical means. For example, you can use the magnet to separate the mixture of powdered sulfur and the iron filings. The magnet will attract the ion and leave behind the sulfur, which is non-magnetic. Many substances studied in the earth science are mixtures, rocks, and soil. For example, are mixtures of many different compounds. The atmosphere is a mixture of gases, including oxygen, nitrogen, and carbon dioxide, and water vapor. Air pollution forms when dust and chemicals are added to this mixture. Dust and fumes from industrial smokestacks and car exhaust from an unhealthy mixture called smog. Seawater is an example of a solution. A mixture in which one substance is uniformly disappeared in another substance. Sodium chloride and many other ionic compounds are dissolved in seawater. The ability of water to dissolve salt and other substances and are related to what you have already read about the distribution of electric charge in a water molecule. The positive end of water molecule attracts negative chloride ions, and the negative end of the water molecule attracts positive sodium ions. You probably think of solutions as liquids, but gases and solids may also be solutions. For example, an alloy in a solution of 2 or more metals. Common alloys include brass, a mixture of copper and zinc, and bronze, and a mixture of copper and tin. Thus I read chapter 8. Finished.